people drifting back in. I will. But you heard me. You heard me, Jana. I'm doing better than you. Okay, we're going to start again in a moment. So come back in. Faces forward. These people. Pencils down. Yeah, not really. Okay, we should start. Yeah? All right, the first talk, we're about to have a measurement session now, which will be, there's 3 very interesting papers. So I commend you to these papers. And I wanted to mention that those who are still here for the whole week, we also have the MAP Measurement Research Working Group, and they meet on Friday. So people who are here giving talks, if you can tune into MapRG and vice versa, this is very good. Okay, so the first talk, I'm Allison Menken, by the way. The first talk is called What Can You Learn from an IP? The paper's by Simran Patil and Nikita Borisov. Simran is a first-year graduate student at UIUC. Nikita Borisov, Nikita here is on the faculty. Simran mentioned that he would consider an internship if people love this paper. Anyway, so Nikita, over to you. Take it away.
All right. Thanks, Allison. So unfortunately, Simran was hoping to come present this talk, but she was just not able to get her visa in time, so I'm going to do it in her stead. So I want to talk to you a little bit about what can be learned from an IP address. And to set the context, if you think back to the bad old days of about 2 decades ago, when we browsed the web in using plain text HTTP. So anybody who can observe your network would be able to see everything you're doing online. They'd be able to see the URLs you're going to, the contents of the web pages, everything. We've come a long way since then. So today, a vast majority of all web traffic is encrypted using TLS. So all of the HTTP messages that are sent by my browser are typically encrypted by HTTPS and therefore are not available to the adversary. But if you look at what a web browser does before it sends an HTTP request, it sends a couple of other messages. It performs a DNS query to figure out the IP address of a web server. And then it performs a TLS handshake to establish secure keys that it uses to encrypt the rest of the connection. And if you look at the transcript of this conversation, you will notice that the domain name that you're going to actually appears 4 different times in this transcript in plain text. In the DNS query, in the DNS response, in the server name indicator extension, in the client hello, and then in the server certificate as the common name. So an adversary isn't able to tell what URL you're going to, isn't able to see the web page you're returning to, but is able to tell what domain name you're connecting to. That said, there's a lot of work going on here and elsewhere to try to remove some of this metadata. So in TLS 1.3, the server certificate is now encrypted. So if you use 1.3, that one domain name instance is gone. If you're using an encrypted DNS protocol, such as DNS over HTTPS or over TLS, like we heard earlier today, the DNS requests and responses are encrypted. And finally, the very last plain text mention of the domain name is in the server name indicator, and there's a draft working group trying to develop this encrypted SNI extension. And so hopefully soon we can get to a world where all of the plain text domain name mentions are gone. The only thing the adversary will see is what IP address you're connecting to. So first, I wanted to mention just very briefly why I think it's important that the domain name be private. A lot of times when you go to Google or Amazon or Facebook, it's not so exciting what domain name you're using. But a number of domain names can be quite indicative of various private attributes, such as your sexuality, your religion, your interests, your drug addiction, and so forth. So overall, I would claim that it's a good thing that we're trying to protect this information from network observers. But, as I said before, the adversary still has access to your IP address. So what we wanted to do is try to understand what does this IP address tell the adversary. And so we performed a measurement study. We started out with the top 1 million sites as listed by Alexa. And we used a tool called MIDA, developed at the University of Illinois, to crawl these websites and get all of the resources that are involved in showing these web pages. So we were able to reach something like 944,000 sites. And these sites requested over 90 million different objects. So about 100 or so per site. These will be various images, iframes, scripts, style sheets, and so forth. You can see a pie chart of what the various object types are. Then we extracted all the domain names that are used in these objects and used them to, used a bulk DNS lookup tool, ZDNS, to get the mapping from these domain names to IP addresses, and then back from the IP addresses to domain names using reverse DNS. So out of these 90 million objects, about 1.8 million domains were used. We were able to look up almost all of them, something think about 95%, and we got a total of about 740,000 distinct IPs. So many domains mapped to a single set of IPs. Now, the first question is, what can an adversary find out if they just use reverse DNS? So reverse DNS is obviously available. If you see an IP address, I can look it up and try to see if I get a useful domain name back. In the vast majority of the cases, this does not give you the looked up domain name. In about 1% of the cases, you do get the domain name that the user looked up. In about 3 or 4 more percent, you get something that is in the same kind of public suffix. So you would get something like server1 facebook.com instead of facebook.com. So you get some general idea as to what's going on. But in 95% of the cases, you either get a DNS, reverse DNS reply that doesn't match your lookup at all, or you don't get any reply for reverse DNS. So we started thinking about a different adversary. An adversary that does basically what we did. An adversary that goes and crawls a bunch of websites to try to get some candidate domain names, then performs a forward mapping on these candidate domain names to get a list of IPs. And then when they see an IP requested by a user, they use these candidate mappings to figure out what domains names these might be. This reverse process relies on the assumption that the user's domain is among the list that was looked up. And so in some cases it will fail, but it will give you a good starting point as an adversary. So the database that the adversary does is a database that we collected, which maps a bunch of domains to a bunch of IPs. And note, very important here, is that different domains can map to more than one IP, and an IP can be mapped to by more than a single domain. And so if we think about the success of this type of adversary in trying to reverse what domain name was looked up, we have to think about what I call the anonymity set of each IP address, which is just a list of domain names that map to it, the in degree in some sense, the in neighborhood of the IP on this graph. So IP2 in this graph has 3 domain names that map to it, whereas IP5 just has a single one. And so this is the result of looking at the IP anonymity sets in our data set. Note there's a log scale on the y-axis here. Almost half of all IP addresses in our data set have just a single domain name that could map to them in our set, which means that under our adversary assumption, the DNS encryption doesn't actually give us privacy of the domain name because only a single domain name maps to that IP. Now, if our adversary is actually trying to figure out what websites you're visiting, which is maybe the higher level task, that's interesting, this doesn't tell the whole story. For example, there could be an IP address like IP5 here that maps back to only a single domain, but is used in a large number of websites. As an example, there's an IP address in our data set that only maps back to a single domain name, stats.g.doubleclick.net, but this domain name is actually referenced at over 100,000 sites in our sample. So seeing this IP address doesn't tell you very much. Instead, we want to see, are there IP addresses that show up for a single website? Only a single site on our list references it. And it turns out that 68% of the IPs that we see have this property. They only show up for a single website. 43% of the websites have at least one resource that has this unique property. And in fact, for almost 40% of the sites, their front page has this property. No other website in the top 1 million has the same IP as the front page of the site. What about the other 60% of the sites? Well, if you look at when somebody loads a website, they go to make a number of connections to a number of servers. So this is a fraction of a trace of loading the web page of the Fairmont Hotel, where we're at. And you see that there's connections made to a bunch of different IP addresses corresponding to a bunch of different domains. An adversary does not see the URLs, does not see the domain names that are being connected, assuming we get to this ESNI world, but does see this list of IP addresses. The question is, how can this adversary map back to a website? Now, it turns out this can be a bit of a complex task because every time you load a site, you might get a different set of domains. Every time you get a domain, you might choose a different IP through DNS round robin, and there might be other complexities. So we don't precisely answer the question of how this mapping back can be done in our paper. Instead, we do a simple proxy. We try to say, for a given site, what is all of the IPs that could be contacted from all of the domains that are in our set? So we could consider this IP set corresponding to each site. And the two sites have different IP sets, then there's at least some chance that you could distinguish them based on their page load fingerprints. And it turns out that almost every website has a distinct IP set in our set. There are a few large clusters, but for the most part, every site is unique. One question you might ask yourself is, why is this the case when we all know that some large fraction of the web is now served by CDNs? Right? Shouldn't there be a lot of convergence of sites and objects to a single place? And it turns out that CDNs generally assign different IP addresses to different domain names. Not necessarily in a one-to-one fashion, but they make use of large IP address spaces. So for example, we did some quick analysis of Cloudflare. They have about 12% of our domains are Cloudflare domains in our data set. So 200,000 domains, but these map to 91,000 different IP addresses, including 3% of all the web pages that have these unique front pages. Right? So this is something that the way that Cloudflare and other CDNs are configured right now, they are not providing any privacy of the IP address they return from the point of view of trying to identify what domain it is. But in theory, this could change. So let me quickly sum up. The I think it is exciting that we're now moving to the place where the DNS privacy could happen. On the other hand, within the context of web browsing, against an adversary who has a pretty good idea of a set of websites you might be visiting, even if the set is quite large, 1 million sites, you get very limited privacy protection from DNS privacy. And so I'll give you some really quick call-outs of our main numerical results, and our final conclusion is that it may be possible to change this, but it will require a change in how the web hosting infrastructure, and especially content distribution networks, are structured. Thank you very much.
We can take a little time for questions.
So you talk about CDNs, right? So if I do a query in Germany for a website and you do it wherever you are, we get most likely redirected. The microphone is off? Sorry.
No, it's fine. Just very hard.
Okay. Huh? Closer to the mic? Okay, sorry. So you talked about CDNs, right? So if I do a query in Germany, I get most likely redirected to a different IP address than you do in the US or wherever you're from, right? So,
yeah,
right?
So actually our attack assumes that you're able to collect these IP mappings from a vantage point that's close to the vantage point that the client is at. Now, that said, it takes it took me about 2 hours to look up the 1.8 million domain names using ZDNS, so I think it's not that hard. But you're right, that you need to be able to localize this database.
You will need to do it per what region or whatever.
Wherever you're observing the client.
Okay.
I mean, one of the things I should say is that a common adversary that people think about in this context is your ISP. In fact, there's been cases where ISPs do traffic analysis of your web traffic to try to insert ads into your communication. There's been a number of places where that has happened.
Hi, Nikita. Dave Blanca. I thought the part of your work about the fingerprinting, about the multiple places people go, was super interesting. And then the comment I have about going forward, about thinking what we can do in the future here, I see you only use these really small IP addresses that have like 3 dots in them or 4 dots in them. What we measure is there are about 2.5 billion of these small IP addresses, the old ones used in the world today. But we see that many V6 addresses every day. So I would love to see this study done on V6, because in V6 you have a lot of liberty as a service provider and as a client to change the prefix length at which you use the address, and also, of course, to change the address on every single thing you do. So me as a V6 client, I could use a different address for every different site I connect to, so you couldn't correlate me going to those fingerprinted sites. And also services could get a lot more liberal about how they choose the address on the other side. And so that's a place we could go with this kind of stuff.
Yeah, that's a very good point. We only studied V4, but V6 could make this a lot better or a lot worse. You could, obviously, there's no reason in V6 for any 2 domain names to map to the same IP address if you didn't want to do that.
Spencer Dawkins, thank you for doing this work. It's very relevant to my previous role, which I am no longer doing. But I did want to ask on your last slide, when you were talking about normalizing IP addresses, is that something that would you might expect would be done in the same way by everybody?
I'm sorry, I didn't hear the last part.
Do you think that would be done in the same way by everyone? Or if I normalize all my IP CDN addresses, is that okay?
The place where it could be done is obviously at the CDN. In fact, I was at a talk by Matt Prince, CEO of Cloudflare, where they talked about actually normalizing the IP addresses that get returned from DNS, right? So when they return their DNS results, they could either return you a random address within their space, or they could just send everybody to 1111, right? I mean, I'm told technically that won't quite work, but something very close to that, an epsilon away from that, would work for their infrastructure.
Okay,
right?
Thank you for helping me understand that last line.
Lars Eggert, yeah, this is really cool and really sort of depressing at the same time. I probably had the same reaction that Dave had. It's like, is it really only the CDNs that can do something here, or would V6 make it better or worse?
Yeah.
Is there something that the clients could do, right? Could you like poison the lookups that you do for a website? Could you throw some garbage in there? Is there anything more that we can do that without like needing to wait for the CDNs?
Yeah, I think it's possible the client could do something like this. So you could, in theory, if you can detect, for example, once again, a Cloudflare IP address, you can actually do something that's akin to what's called domain fronting and just pick a different IP address in the Cloudflare space. As long as you send the right SNI and you can send an encrypted one for Cloudflare, you can do that. So there's some opportunities to do something like that. The data, I'm happy to share it. I haven't put it online because it's about 100 gigabyte database. But if somebody wants to look at our CDN analysis is actually the reason we look at Cloudflare is that they have a list of all the IPs that they use. We'd love to do the same analysis for their CDNs, but the tools we found for detecting which CDN is being used so far have been kind of not so good. So if anyone knows good ones, please let me know.
Lorenzo Coliti, I was thinking about a mobile device running several different apps at the same time, and my unsubstantiated intuition was that it probably doesn't take much in the way of noise to make this stuff actually stop working.
I think that's a good point. So if you look at this page load fingerprint, this is in some sense similar to the process in traffic analysis that we call the website fingerprinting, where instead of looking at IP addresses, you look at traffic shapes that are doing in there. And in that area, there's a lot of research right now that actually looks at this question of noise and what kind of noise you can add and what kind of ambient noise, do these things actually work? For example, trying to identify when you even start looking at a website versus, if you come in the middle and
right.
trying to partition things, or if you're browsing in multiple tabs. So yes, that's true. The exact extent to which this would work in a fingerprinting context will vary, and then maybe some of the techniques that people use to identify, to try to improve website fingerprinting, to do the partitioning or other kinds of, analysis under uncertainty could be used here. But that's not something we've investigated in depth.
So a client could simply just connect to a bunch of other IP addresses.
Right. So you could definitely add noise to this as well. It doesn't really help unless you have a good noise model, in the sense that, if you have some very sensitive site and you're accessing an IP that only belongs to that site, what are the chances that you would have picked that through just random connections? Getting good kind of background noise models is hard, but I'm not saying it's impossible.
The other question I had, did you look at Google site specifically? My knowledge of Google is a few years out of date, but I used to remember that there was a total of, an equivalence class of maybe 60 IP addresses on which everything goes.
There's definitely
very different from Cloudflare.
A bunch of equivalence classes for Google IP addresses, but I haven't looked at specifically.
Okay. Hi there, Daniel Kahn-Gilmore from the ACLU. So thanks for doing this work. It's really good to see the problem stated as clearly as I think you've stated it. There have been a few comments in the mic line here about what could the clients do differently, what could the CDNs do differently. And I'm wondering if what you've looked at has given you any insight also into what the individual website operators could do differently. So for example, should you limit the number of third-party parties that you load resources from, or should you not limit the number? Or have you thought about that, or tried to model things, best guidance for website administrators?
That's a great question. Obviously, the first step is hosting your first-party site somewhere that has collisions with other websites. But then about the third-party thing, it's interesting because in some cases, adding more third parties might help because you get more intersections. It's not something we've looked at specifically, but yeah, I think it's definitely interesting to think about it from all three perspectives, like you said, from a CDN perspective, from a user perspective, and from a web server website perspective. Thanks.
Great. Let's thank the speaker again and the other author as well. Thank you. Next up is Chris Misa, who is from University of Oregon. And this is a paper called "Can We Containerize Internet Measurements?" And Chris says, first year PhD students, so again, possibly internships rather than you should think about grabbing a person for your employment. And there's several other authors I think you'll mention, but thank you. Hopefully this works now. Can we containerize connecting up machines to...
All right. Is this...
Can people hear?
Can you hear me if I speak like this? Okay, cool. It's about the right height. We'll just go with it.
You can change the height a little bit if you want.
No, I think it's fine.
Okay.
So we'll start with this question, can we containerize internet measurements? And this is a joint work between myself, Sudarsun Kannan from Rutgers University, and my advisor at the University of Oregon, Ramakrishnan. So we'll go through this question in three sort of distinct phases. The first, we'll look at some of the issues around containerization, and we'll talk in particular about what containerization means for internet measurements. And then we'll look at a proposed solution that we've developed called MACE, and we'll also present an evaluation of our solution. So first, I'd like to give just a brief sort of run-through of what containers are. They're essentially a new, relatively new isolation mechanism that allows us to run applications in isolation using a single kernel. So rather than a VM where you have to run an entirely different operating system for each application, you can run the same operating system, but we use these recent sort of developments in Linux and other OSs to achieve isolation between the processes of an application. Namespaces allow us to isolate what application can access, and C groups allow us to allocate resources to those applications. So you can give a particular application a certain share of CPU cycles or particular memory access or particular NUMA node affinity. And containers, due to some of these advantages, they are rapidly replacing VMs and cloud computing settings and high-performance computing as well. There are a lot of different sort of software deployment settings are using containers now because of the advantages and because of the utility of having convenient packages. So for internet measurement, why do we care about containers? And the reasons are fairly similar to the reasons any application developer or deployer might care about containers. They allow us to streamline experiments, the deployment, the sort of packaging, the standardization of them. So scripts, tools, libraries, even like if you have data sets that are required for doing inference or lookups, they can all be packaged into a unified container image, which we can then deploy through consistent container runtimes on a number of hosts in a wide variety of different geographically diverse or topographically diverse locations. So this exposes new cloud native vantage points, Azure, AWS, Google Cloud Platform, and a number of others. And of course, internet measurements also benefit from having less CPU and memory overheads compared to VMs. And this little ghost that's been hiding on the right of this slide is a reference that Planet Lab has actually been using LXC containers as their experiment allocation unit since 2012. So to answer the question we started with, sure we can. I mean, it's already been being done in Planet Lab, for example. But we want to look in this study at why not. In other words, whenever you virtualize something, there's going to be overheads. So if we're virtualizing something using containers, what are the overheads? It's not enough to say, oh, they're a perfect solution. In particular, containers give you pretty good usage of CPU and memory compared to the native host installation of an application. But due to issues of network isolation, you incur extra latency in the networking layers. And we've measured this in this study, and it kind of confirms results from other studies that this is around 50 microseconds in resting systems. But the key issue that we identify, we want to bring to people's attention, is that when you add multiple containers on the same host, this latency overhead increases. We've measured it up to 300 microseconds, depending on traffic. And if you continue to add containers, you can kind of continue to push this latency overhead higher. So if you're doing any measurement that deals with timing, so if you're trying to measure RTT or one-way delay or do inferences based on timing, you have to deal with this in a container. You have to deal with these non-constant latency overheads. And we observed that there's a lot of work that's going into kind of trying to solve this problem of the latency overhead in containerized network virtualization systems, such as SLIM and FreeFlow, but these efforts, for the most part, don't really have any benefit for internet measurement. SLIM in particular uses flow-based virtualization, and FreeFlow requires specialized RDMA hardware and drivers on both endpoints. So in the context of internet measurement, neither of these solutions are really very useful. So just to give a sort of illustration of latency, this number 300 microseconds probably doesn't mean a whole lot, but the speed of light is in a roughly 90 kilometer air radius. So if you're off by 300 microseconds, you're off by like 90 kilometers. And I've drawn a circle around Montreal, so it reaches down into the United States and several other cities and towns around Montreal and Canada. And using this number is calculated actually from Amazon's latency statistics. They calculated a particular rate at which they lost sales money per millisecond. And so if we translate this into our latency, we're talking about an error of about $1.2 million. So if you're trying to estimate how much is this link going to cost me, or how much am I going to lose if my latency increases, that's the margin of error you're talking about. Additionally, it's hard to isolate these kind of latencies between if you observe a latency from a particular application, there's nobody you can ask right now, like, where is this latency coming from? Is it the physical network? Is it the operating system? Is it the application? Is it the virtualization layers? So we're addressing in this study how to account for these latency overheads in a running container system. In other words, we want to do this in real time. We can't do this as a static thing because it's going to be changing as new containers are deployed on the node, or as the traffic characteristics of the containers that are running on the node change. And so to address this, we've developed a solution which we're calling MACE, standing for Measure the Added Container Expense. So we imagine containers for measurement running in a typical sort of bridged or overlay container network virtualization. So as drawn on the right, you have an interface that's in the container's network namespace. That's the ETH0 at the top, and then you have layers of bridges and routing so that packets eventually traverse an interface on the node, on the host node. That's the ETH0 at the bottom. And so the goal of our solution is to measure that red dotted line. So we want to know how long does it take a packet to go from the container to the host. For ingress and outgress, we want to do this per packet, and we want to, of course, have high accuracy. Additionally, our goals in developing this solution are we do not want to incur additional latency in the virtualization layers. So often when you start probing things, we'll talk more about this later, when you start probing things, you tend to increase the latency, but we want to minimize that impact. And finally, we want a container-friendly interface. So we want your container to be able to ask, what are my latencies to the outside world in real time, whenever it pleases. So the method that we've developed to do this uses Linux kernel trace points, which are essentially hooks into particular lines in the kernel source code. You can insert your own probe functions into those lines and really muck things up if you don't know what you're doing, or put them to good use, as we are attempting here. So we have, in particular, I've circled in red the ones on this, on Brendan Gregg's excellent diagram. So we have trace points in the system call interface and also at the net device layer. So between those two, we can actually access sort of both the system call layer, which is the applications running in the container, so that's kind of the top of that dotted line, and then also the net device layer, which gives us access to closer to the bottom. We have some ideas about how to go further down into the hardware too. We originally had implemented this solution using existing tracers, such as ftrace, and so this is, of course, the logical first step. What we notice is that these tracers are great for doing sort of diagnostic stuff. If you have a problem, you spin up the tracer, you figure out what's going on. But if you want to run them as like a monitoring solution, they're really terrible because they have this huge perturbation on the system. And moreover, what happens if you do a trace is you have an enormous amount of trace data that gets spit out, and you have to somehow store that, filter through it, and distill it into the actual latency results that you care about. So due to this, we've developed an application-specific kernel module specifically for monitoring this virtualization latencies. And we imagine that this is a module that you could run on container hosts that care about doing this kind of measurement. And it reports directly to containers' namespaces. So this solves the other goal of how can we make a nice container-friendly interface. So we'll go through the design of this module really quickly. Essentially, we have packets egressing and ingressing the virtualization system on the top. And these packets trigger the trace events. So the 4 trace events that we are actually probing are listed next. Sysenter and then netdev start xmit for the egress path. And what we do is we filter these events. So we only listen to particular interface. We only register events on particular interfaces that we're listening for, that we care about. And also we only register events in particular namespaces that we care about. So we're already doing some data reduction at that level. Next, we correlate events. So we have to have correlation. Each packet incurs a whole series of events as it passes through the virtualization layers. So to be able to correlate which events map to which packet. And we do this using hash tables for both ingress and egress. And finally, we push latencies into these ring buffers. And we maintain a ring buffer per network namespace so that your container, when it's asking for latencies, is basically just doing a simple read of a ring buffer that's allocated for its network namespace. And these are accessible via device special files. Okay, just a couple more implementation notes. We're using the TSC for accuracy and low overhead timing. We minimally lock everything, so we're using atomic types for the most part to deal with these the lists and queues that we have to maintain. And we have a consistent namespace aware API. So when you read from one of these device files, it basically checks which namespace you're reading from, and depending on that, it will give you results for your namespace if your namespace is being actively monitored. And this is all open source. The link is there. We'll make these slides available publicly later. So if you want to check out the source code, if you want to help us, there's a bunch of sort of points later. If you want to help us continue developing this, that would be excellent too. So just to give you a sense of the interface, I'll go through the steps involved in running this from a container, assuming the module is already loaded on the host. So the first step is to basically echo a non-zero value into this as one of these sort of sysfs control files. So this basically tells the module, okay, this namespace, whoever is echoing this non-zero value, wants me to monitor their ingresses. So then it sets up the necessary ring buffer and everything to do that. Next, you execute. I guess I have to kind of point this over there. Next, you execute your experiment. So maybe we're just looking for the RTT to the nearest host that's going to call themselves google.com. And finally, you collect the latencies. So this is as simple as reading from a device file, which basically exposes the ring buffer that's allocated for that namespace. And for now, we're kind of just reporting latencies in this nice, mostly human-readable format. There's a timestamp. We've implemented this so far just for ICMP, so there's an ICMP sequence number. And then it shows you the egress and ingress latency in nanoseconds on the far right. Well, let's not skip that many slides, please. So how do we know these numbers are correct, right? You get these sort of cryptic-looking integers, and we say they're nanoseconds, but why would we ever trust that without some substantiation? So we have so far executed a relatively primitive, but we feel it supports the accuracy of our tool sort of evaluation. The issue is there's no direct method. In other words, we can't directly observe what we're trying to measure because in order to do that, we would again be incurring additional perturbation, and the actual thing that we're measuring would be changing. So we develop a method, and it looks like the right side of my slide here is cut off, but that's okay. Don't need it. We develop a method which basically evaluates the accuracy of our latency measurements by evaluating the ability for us to take a RTT measurement from a container and compare it with an RTT measurement made from a host. So what we want is we want to be able to use our latency measurements to subtract the latency overhead from inside the container and to create containers that can take measurements as accurate as those made on the host natively. So to do this, we first take the RTT from the container, then we gather the latencies computed by Mace, and then we subtract the two, so we call this the corrected RTT, and then we compare this to a ground truth RTT of the network, which we use hardware timestamping to achieve. So our evaluation does this over a single link, and to minimize the network effects, of course, we're interested in the virtualization overheads here, so we want the network to be as quiet as possible. we add co-located containers on the measurement, on the host that's running the probe container. And this is because of our observation earlier that having multiple co-located containers and extra traffic going through the virtualization system actually changes the virtualization system's latency effects. So these containers are running flood ping is kind of a worst case scenario where you're running this measurement container on a host that's very, very busy. And these run on Cloud Lab, so there's a little bit of noise from the experimental network overlays that Cloud Lab uses, and also on the sort of accounting agents that are running on Cloud Lab nodes. So this is our main result is presented here. This is RTT bias. So it's the difference between the reported RTT from one of these sources and the actual RTT as measured in hardware. So the blue trace on the top is the RTT that's reported from inside the container, the raw RTT without any modification. So, and it's cut off here, but the x-axis is the number of traffic generating containers that are running co-located on the same host. So you can see even with just 30 other containers running on the host, we've already incurred, over 300 microseconds of additional latency on our measurements that are taken from inside the containers. And to compare this with the sort of native versions, we have the green and the gray trace. So these are native references that are taken from the host. Of course, they're not without their own overheads, so there's a little bit of a bias between them and the hardware RTT. And then we finally show the container corrected result, which is the black trace. It's visible above the green and gray traces there. So that's the one that we described previously as being the RTT taken from the container with the latencies subtracted. So in other words, after we've accounted for these latencies using MACE, we're able to estimate the same RTT result that we would get from running the process natively to within 20 microseconds in the worst case. And another observation here, the sort of secondary, is that all traffic or all of these RTT measurement tools are impacted by the addition of extra traffic going through the virtualization layers. So it's not just tools that are running from the container. Whenever you're running a tool that's measuring RTT, if there's extra traffic either going through containers on that host or other processes, you'll notice that you'll get different, you'll get some bias in your resulting measurements. So because we're using hash tables, I'll go through this pretty quickly. It's just sometimes we get hash collisions, which causes us to lose particular packets as we're correlating them through. So we report sort of coverage, which is the number of latency reports divided by the number of packets as a percentage. And this plot is a little bit scary when I first drew it, but then I realized the bottom line here is actually 95%. So we're doing okay. We noticed that we can kind of solve this problem by adding larger hash tables. So if your hash tables are larger, you get less collisions. So there's kind of a trade-off between how much memory you want to allocate for the MACE system and how much coverage you want, how many of the packets that you actually need RTT reports on. So to address one of our other goals, of course, minimizing perturbation, we measure perturbation as the difference between the instrumented RTT reported and the RTT without instrumentation. So this is basically we just discard the latency results from the measurement, but we want to see how does inserting this tool affect the RTT results. And so we compare ourselves with ftrace so far. So the blue and the green traces on this chart are ftrace running from the container and from the native context respectively, and the black and the gray traces are the same perturbation calculation, but taken with our solution MACE running instead of ftrace. So what we notice is that as there's more traffic, the ftrace perturbation increases significantly. And so this is actually an effect that all traffic on the host would see, even traffic that was not associated with the measurement from running ftrace. So this is, again, goes back to this point why we don't want to use these generic tracers for this kind of application. But we noticed that MACE scales decently, it scales better. So there's a couple of blips, but for the most part, it's below 20 microseconds in terms of perturbation. So it's still 20 microseconds, and we think it's serious enough that we want to continue sort of optimizing our code. And so to that effect, we've run some initial evaluation of the runtime of the different components of MACE, which is presented here. So on the left are the bars. Again, the bottom is cut off a little bit here, but the group of bars on the left represent the results running in the container from a measurement running in the container. The group of bars on the right represent results running from measurement from native space. So then within that, the subgroup on the left, there's 4 bars, the blue, red, yellow, and light blue bars. Those are the system trace probes. So we notice that they're hit the most, and they're also the slowest running functions. So we want to kind of focus our efforts there. The pink and purple bars are the functions responsible for managing the ingress and egress correlation hash tables. And the green bar is the function responsible for pushing events into the namespace ring buffers. So we notice that the system call trace points are the slowest, and this is because our current correlation scheme actually requires those system call trace points to do copies. They have to copy data basically back from user space because we don't have a convenient way to access it from the system call trace probe. So there's some implementation things that if we improve the implementation slightly, we might be able to get rid of a lot of that overhead. Go through our goals for the future of this real quickly. We want to add TCP and UDP support, of course. We're just doing ICMP for now, but you could imagine that ICMP is a small fraction of what internet measurement cares about, and we want to be able to use this with things like Scamper TCP ping or UDP ping. We're looking at using hardware timestamps. These are available pretty commonly on a lot of current NICs. And if we can use hardware timestamps, then we can account for not only the virtualization latencies, but like all of the latency that's incurred when you're sending packets down to the hardware level. We need better in-flight correlation. As I was saying earlier, the correlation that we're using right now requires these really expensive copies. So we need to either stick stuff on the SK buffs or find some other correlation scheme. And we also need to address the ease of application level correlation. So what I mean by that is you saw earlier we're reporting ICMP sequence number, and the reason that we have to do that is because otherwise it's very, very hard to connect the latency result that you get if you're doing per packet latencies to the actual packets that you were sending. We tried just using timestamps, and the accuracy was just too far off at that time scale. So thinking about using TCP sequence numbers or some other application layer correlation. The other thing that's possible is that since we're doing processing in kernel space, we could also be running threads that would be calculating like aggregation functions over latency. So we could be doing moving averages, we could be doing minimums, maximums, histograms, or other things. Again, these are just things to tack on to the implementation. We're also looking at applying this tool. So we want to use it to see if we can improve measurement accuracy significantly for like geolocation or estimation of costs and for businesses that care about latency. And we also want to start working on developing virtual network telemetry systems. So this is a big issue that I was talking about earlier. When you observe a latency in your network, especially under virtualization, these days it's very, very hard to know who's responsible. So we want to kind of use MACE and some other tools and maybe kind of integrate them into a large-scale virtual network telemetry system that would answer those questions. So you could ask, where is this latency coming from? It'll be say, oh, it's the bridge network or it's the overlay network. So that's another sort of destination for these results as far as we know. If there are others, let me know. We're open to whatever. So in summary, we presented some of these issues, we proposed our solution, and we showed the evaluation of our solution. So thank you. This work is supported by the UOVPRI, NSF. I'd like to thank the anonymous viewers for their feedback, and also the Cloud Lab team for maintaining this great public resource. I'll be happy to take any questions.
I think we'll just take one question if someone has one. I should have thought of one. Okay, I think that was very good storytelling, so thank you. And a very good talk. Thank you so much. Okay, finally, come on up. And our last speaker, and I just have a terrible memory, so I have to look. Sorry, Danny. Is Danny Latos, who is from the University of Campinas, Unicamp in Brazil. And this is a talk about an IETF protocol supporting multi-domain use cases with Alto. Hopefully we can get you on. It looks like things are going to work. Oh. looks good. Getting there. Okay. Okay.
Okay. Thank you so much for the introduction. This is a joint work with people from Yale University, Ericsson Research, Nokia Labs, Spring, and Telefonica. So the rationale of this talk is to try to summarize the current standardization efforts into the IETF application layer traffic optimization working group to support multi-domain use cases. And then the idea is to provide key main requirements on network information exposure to support such multi-domain use cases. And finally, provide information about new and novel mechanisms and abstractions to improve the base ALTO protocol to support multi-domain scenarios. Oops. Okay. So the ALTO protocol provides network information to the application in order to try to improve, maintain the application performance. Basically, the network information is exposed as an abstract maps, network maps, code maps, unifier property maps, etc., in order to try to protect the information privacy and improve the scalability. The origins of the ALTO protocol are peer-to-peer application, where a host is a peer trying to connect with other peers for file sharing or real-time communication, but or however now ALTO is being to be considered as another multi-domain scenarios such as data center network, content delivery network, etc. ALTO provides an information publishing interface between an ALTO client and an ALTO server. Here, for example, we have a couple of scenarios where an ALTO server and an ALTO client can be placed in a peer-to-peer topology network. An ALTO client can be a peer-to-peer client application, or can be a resource directory in a such as a BitTorrent tracker, for example. In the later case, the peers are not able to request information directly to the ALTO server. Instead, the resource directory requests information to the ALTO server, and after will provide information to the peers. Currently, the ALTO provide a generic architecture to provide network information for application. In this picture, we have a high-level overview of key ALTO mechanisms and abstractions. For example, the ALTO mechanisms, we have the information resource directory that allow to provide information about the available information resource directory. We have the information consistency to specify the dependency between different information resources. We have an information update model to string control, push, and incremental update of the information resources. And also ALTO introduce abstraction modules, different abstraction modules such as a network map and cost map, in order to allow network location grouping and a cost between them, the patch vector abstraction to provide a more detailed information about the routing using abstract network elements, and capability maps to provide unified property maps and footprints capability. So this is an overview about the current ALTO documents. We have 7 RFCs. For example, from the problem statement and the requirements, it was defined the base ALTO protocol, and there are three other RFCs related to the server discovery, deployment consideration, and multi-cost map. There are 7 internet drafts to extend the base ALTO protocol, and there are a set of individual drafts, some of them related to multi-domain scenarios. Here I am including some potential future topics that under discussion to be considered. Some of them related to extension for new architectures, extension for new settings such as NFV, HCloud, or the integration of the information model and control model. And the idea is also to resume the ALTO survey in order to map the current ALTO implementations in real use case scenarios. So currently, multi-domain use cases are emerging with the development of new technologies such as FDN, NFP, or 5G. So, example of such use cases including multi-domain collaborative data science, multi-domain flexible interdomain routing. In the past few IETF ALTO meetings, different individual drafts were submitted summarizing the experience of developing multi-domain application using ALTO. Here we have an incomplete list of them. So related to the multi-domain collaborative data science, here we have a couple of examples on premier scientific experiments. For example, the Large Hadron Collider and E-square kilometer array. Such experiments push scientific discovery boundaries and rely on workflows that coordinate geographically distributed resources. Here we have an example of the movement of the LHC data from Tier 1 to Tier 2 and Tier 3 storage sites. This type of scientific workflow use multiple domains with heterogeneous resources to run different application of jobs. So the key requirement in this type of distributed workflow is the ability to orchestrate multiple resources across multiple domains for heterogeneous applications. Related to the multi-domain service function chaining, an end-to-end network service often requires physical or virtual network function in a specific order. Currently, network operators start offering to the customer the possibility of configuring network services with specific resources and performance. Such resources are expected to be available across multiple domains with different technologies or different administrations. As I mentioned, an end-to-end network services is composed by a set of virtual network functions and a set of paths. So the deployment decision problem involves to discover the best candidate domains and the best feasible paths to connect such domains. In order to take optimized implement decision, network management need to maintain a network inventory in order to get a real-time representation of the available network infrastructure resources. Once the network inventory is built, an information publishing mechanism is also necessary in order to the network inventory can provide an information to the management system. Network providers, here we have another potential multi-domain scenario where the network providers are expanding the granted capability of SDN from intra-domain setup to multi-domain settings to provide flexible inter-domain routing. Traditional inter-domain routing protocols are limited because usually they provide a single path routing or limiting the client's path choices. So flexible multi-domain routing allows to the user to specify a routing action at the provider network. This is with more flexible matching condition and more choices on routes so that the network provider can expose not only currently used route but also available yet unused routes. Here we have a couple of requirements for ALTO to support new multi-domain use cases. Modern use cases require information on properties and capabilities of different network resources, including transport resources, processing resources, and storage resources. So these use cases need to orchestrate multiple resources in multiple networks so that a unified representation of capabilities of multiple resources is a key requirement for multi-domain network information exposure. And existing representations tend to focus on single domains. So in multi-domain use cases, that related information can be retrieved from multiple networks to compute end-to-end information. As such, abstraction that support aggregation of multiple networks into a single and virtual network is another key requirement. So in order to the multi-domain abstraction is used to solve the application layer optimization across multiple domains. Typically, previous use cases can be modeled as optimization problem F, where F is an optimization function based on two types of variables, X representing the network parameters and Y representing the application parameters. Such objective function is also contain two types of constraints, X representing the networking constraints and Y representing the application constraints. The lack of full acknowledgement or control over the network limit the potential values of X, for example, bandwidth, delay, packet loss, etc. So the multi-domain networking abstraction is aiming to at providing such constraint in order to solve this optimization problem. What is the basic formulation? Application interact with network by asking to carry traffic for a set of flows. In this example, we have two flows, F1 and F2, that will travel different networks. Each flow has a set of properties, for example, paths representing the sequence of network device that the packet of flow will traverse, delay, available bandwidth, etc. In a multi-domain setting, a network property may involve network properties of multiple components. For example, in case of the delay property in a multi-domain setting, should be the sum of the delay property in each network. So the basic idea here is to provide the ability to discover, aggregate, and expose information of multiple domain networks to provide a single, consistent and virtual network view and represent that information using a generic, compact mathematical programming constraint. So to give an illustrative example, here we have a user that want to request to circuits, for example, from source 1 to destination 1 and from source 2 to destination 2. Both circuits share a common links, link 3 and link 4. So that is not possible to reserve 100 gigabits for both circuits. Using the mathematical programming constraint, we can generate linear inequalities to provide a compact representation of the available bandwidth of flow through a network. For example, here, X1 and X2 represent the available bandwidth for flow 1 and flow 2 respectively. So this resource abstraction represents the resource feasible region of the network for providing resource to a set of flows. As such, some linear inequalities can be redundant. The redundant inequalities are removed using a polynomial time optimal algorithm. Taking the previous example from a single network to a multi-domain network, here we have a collaborative network with 3 member networks, and a user want to request. Oops.
Well, so Danny, I think we'll have to get that back, but also, can you wrap up in about a minute?
Yeah.
Okay. Huh. Or maybe it was. Maybe you can tell them what the info is. Can you kind of come to all right, well, come to to some of your conclusions without the slides?
Yeah.
Okay. Because we want to wrap up in about a minute. We've got some closing remarks too. Okay. So.
Yeah. Just to summarize, the idea was to try to to show the current standardization efforts into the ALTO working group, and provide new design requirements to improve the base ALTO protocol. And as next step, the idea is to give into the more experimental evaluation to the multi-domain scenarios. And lately, the idea is to try to invite you to the ALTO session that will be placed this Thursday at 10 a.m. And we have also several regular weekly meetings every Wednesday. Also, you are welcome to join us. That's it. Thank you.
Thank you. Let's thank the speaker. That is a hard problem to tackle, so thank you for presenting that. I think Colin wants to make, let's have, if there's any one question, we can manage one. Otherwise, we're going to turn it back over to the IRTF chair, Colin, for his closing remarks. Oh, Philippa first. Okay. All right, so thank you very much.
Well, not too much